Let's get going. So this week we're going to continue to talk about hierarchical models, which is basically to say we're going to talk about models because pretty much any model that you would estimate using Stan is going to be hierarchical in the sense that we talked about originally, where a hierarchical model is just one where your prior distribution on some parameter depends on another parameter, and you have prior distributions on both that imply a joint prior distribution for those unknowns, and indeed all of the unknowns that you're thinking about in your model. We're going to talk a little bit about how to do this more in rstanarm. Also this week, we'll be talking about how to use another R package, which provides an alternative interface to modeling things with Stan. It's called the VRMs package. So before doing that, we have to say that Columbia developed Stan. It's seeking additional money to continue to develop Stan. I use Stan for business purposes, and that creates a conflict of interest, even when mostly talking this week about VRMs, which is a package written by someone who is not an employee of Columbia University, and yet this conflict of interest thing still applies. So remember, when we're thinking about a hierarchical model, at least in the base case, we're thinking about, okay, you have parameters, beta, that are specific to the jth group. Now, that could just be a single intercept, in which case k is 1, and this whole thing simplifies. But in general, you could have coefficients, intercepts, all that thing, varying from one group to the next, one state to the next, one, other sort of classification of your data. And we're thinking about these, at least if we're thinking about this from a Bayesian perspective, is having a multivariate normal prior on these groups, this vector of k parameters that are specific to group J. And that multivariate normal prior is going to have a global mean vector mu and a variance covariance matrix sigma that describes how these k vectors that are specific from from one group to the next vary around the overall mu across all groups in a multivariate normal fashion with variance covariance matrix sigma. And so if we're taking a Bayesian perspective on this, which we should be doing, then we're going to have to specify a prior distribution on the mean vector mu and the covariance matrix sigma. A lot of people, I think, avoid taking the Bayesian perspective on this because specifying a prior on the k by k covariance matrix is a difficult thing to do, and so people sort of naturally incline to go with LME4 or proc mixed, or there's mix something in Stata that are going to estimate these models from a frequentist perspective and not put priors on mu and sigma, although they're going to maintain this assumption that beta sub j, or at least part of beta sub j, is part of the error term, and so they can make multivariate normal assumptions about it. It's worth pointing out that the reason why frequentists use multivariate normal distribution for the group's deviation from the population parameters mu is because the multivariate normal distribution is the only one with distribution on these error components, which combined with a normal distribution on the observations means they can analytically integrate the group-specific parameters out of the likelihood and then maximize the likelihood with respect to the common parameters mu, sigma, etc., or what they refer to as the fixed effects. Now, if you have like a logit model or something for the observations, something where you're not using a Gaussian likelihood, then even if you put a multivariate normal prior on these group-specific components of the error term, you're not going to be able to analytically integrate them out of the likelihood anyway, and you have to use numerical integration techniques or sampling techniques that are very similar to MCMC in order to even evaluate the likelihood and then choose the population fixed effects to estimates thereof to maximize it. And so there's not really that strong a case for using multivariate normal. Of course, from a Bayesian perspective, going to be using MCMC, specifically STAN. And so you're free to use some prior distribution on the beta sub j's that's not multivariate normal. And it works basically the same, whether your likelihood for the observations is Gaussian or it's binomial or it's Poisson, whatever. But definitely multivariate normal distribution is about the most complicated multivariate distribution that most people can handle on their best day. And so you don't see a whole lot of people, even Bayesians, departing from this idea of using multivariate normal priors on these group-specific parameters. Anyway, if multivariate normal is about as much as most people can manage, then it's even more complicated to try to specify a prior on sigma, which is multivariate, but it's a covariance matrix rather than a vector of coefficient. That makes it harder because it's not even specifying the prior is that difficult, although it can be. Specifying the parameter space for a covariance matrix is a difficult thing to do because you have k choose 2 plus k free elements along the diagonal. They have to be positive, but you have to choose the other k choose 2 elements in the off diagonal of a variance covariance matrix in such a way that the entire variance covariance matrix satisfies the positive definiteness restriction, which is basically a multivariate inequality, a whole bunch of things being positive. We talked about that last week when we talked about obtaining a Cholesky factor of covariance matrix. If the covariance matrix is a proper covariance matrix, which is to say it's positive definite, then its Cholesky factorization will exist and be real. But remember that Cholesky factorization involved along the diagonal of the Cholesky factor the square root of a bunch of stuff, which is a complicated function of sigma. And so that number under the square root has to be positive in order for the Cholesky factor to be real and thus for the covariance matrix to be legitimate. So even specifying the parameter space, the collection of these k choose 2 plus k elements that satisfies the positive definiteness restriction is already way too much for most people. And then to try to specify a prior distribution over that space that reflects their beliefs as to what sigma might be is really, several bridges too far. When you look at the earlier Bayesian literature on these hierarchical models, you'll see a whole lot of so-called inverse Wishart priors being specified, which are got to be one of the more confusing distributions out there, maybe except for the negative binomial. But the inverse Wishart distribution is conjugate with the multivariate normal. And so you can do Gibbs sampling, or you can work out the full conditional distributions analytically. The posterior distribution for sigma would also be in the inverse Wishart family if the prior distribution is in the Wishart, inverse Wishart family and everything else is normal, etc. So with STAN, we're not using Gibbs sampling, and thus we're not constrained by the so-called requirement of being able to work out the full conditional distributions of these parameters analytically. The proposals for the parameters are all joint, and so you're free to do what makes sense. Now, for a lot of people, it's open question as to what would be sensible, but for a starting point, typically with Stan, you're going to want to decompose the variance covariance matrix sigma into a diagonal vector of standard, or diagonal matrix of standard deviations delta, and a correlation matrix lambda. Both the correlation matrix and the diagonal matrix of standard deviations are easier to reason about, easier to come up with good priors for, than for covariance matrix like sigma as a whole. And if we can specify priors on the diagonal elements of delta and the correlation matrix lambda, then that implies some beliefs about sigma that are reasonable if our beliefs about delta and lambda are sensible. So to start with, we're going to decompose sigma in this way. And then there's a question, okay, what should we use for the diagonal elements of delta? One approach is, okay, so the diagonal elements of delta are the standard deviations for the kth element of the multivariate normal distribution that we're talking about. And what is done in rstanarm is to write the squares of the diagonal elements of delta, which is to say the variances, as equal to tau, which is unknown, times pi sub k, which is unknown. Okay, so I've taken my unknown variance and I've written it as the product of two more things that I don't know. So how would I specify my prior beliefs about tau and about pi k? So tau is going to be constructed as the trace of the variance covariance matrix. The trace of a matrix is the sum of its diagonal elements. So in the case of a variance covariance matrix, a trace is the sum of the variances. And in truly hierarchical fashion, we're going to write that as a product of two things. One is gamma squared, and the other is k. Now, at least we know what k is. That is an integer specifying the size of this multivariate normal distribution. Could be 2, could be 4, could be 1. But in general, it's going to be more than 1. Okay, so now we have simplified the problem. If we can specify prior beliefs about gamma, then we have characterized our prior beliefs about tau, where tau is the trace of the variance covariance matrix. And so the prior used in rstanarm on gamma, which is basically a scale parameter, is the gamma distribution. And you choose the shape and scale of that gamma distribution. But by default, both of those are 1, implying that the prior distribution on gamma is in fact an exponential distribution with expectation and a standard deviation of 1. Again, exponential distribution is pretty popular for parameters that are constrained to be positive because it is the maximum entropy distribution among distributions defined over the positive part of the real line, conditional on the expectation only. Okay, so we have a prior for gamma. Tau is equal to gamma squared times k, and we know what k is. So we've characterized our prior beliefs about tau via gamma. And delta sub k squared, which is the kth variance, is equal to tau times pi k. And so what are our prior beliefs about pi k? Well, the entire collection of the elements in the vector k is a simplex vector, which is to say they're non-negative and they add up to exactly 1. So if tau is the trace, which is the sum of all the variances in a variance covariance matrix, and pi consists of numbers that are non-negative and add up to 1, we can think about pi k as being the proportion of the total variance that is attributable to the kth variance. So it's basically delta k squared as a proportion of the total variance in the variance covariance matrix. That's how we would interpret pi, as a proportion of total variance. And simplex vectors are relatively easy to reason about. Certainly the most common prior for those is the prior, the guy's name I can't pronounce, but it has shape parameter or shape vector A. And if A is equal to 1 for all k elements, like we talked about last week or 2 weeks ago, then that prior is going to be uniform over all simplex vectors of size k. And so just by specifying A is equal to a vector of 1s, then we can have uniform prior beliefs about pi, which again is going to be a maximum entropy distribution. We could take A to be numbers a little bit greater than 1. That is going to tend to express prior beliefs that the elements of pi are closer to 1 over k. We can specify A to be numbers less than 1, but then it has this sort of U-shaped thing on the margins of pi, which is usually a pretty weird thing to believe. Again, this distribution is a generalization of the beta distribution to more than 2 dimensions. And so your intuition as to how to specify a prior on a single proportion or a single probability mostly carries over to this generalization where we have multiple things that are between 0 and 1 and add up to 1. Okay, so that covers us for pi, for gamma, consequently for tau. And now we've expressed our prior beliefs about the diagonal elements of delta, or at least their squares, which are their variances, but we can easily take the square root of those and put them on the diagonal elements of delta before multiplying on the from both sides interior the correlation matrix lambda. So at this point, we might say, well, how can we express our prior beliefs about the correlation matrix lambda? And we'll get to that on the next slide. But what this exercise hopefully, and it'll become clearer once we get to the prior on the correlation matrix, this idea of decompose into smaller parts that are easier for you to wrap your head around, and or until you get into a position where you can put a distribution that is at least easy to defend. There's not going to be a whole lot of objection if you're using, A equal 1, and so you have uniform beliefs across simplex vectors of size k. But that's a pretty reasonable prior. We have a pretty reasonable prior for gamma. We'll show in a second. We can have a pretty reasonable prior for lambda. And if you have pretty reasonable priors on these pieces, then your prior beliefs, when you combine them up into the whole about sigma, are also definitely going to be entirely adequate for you to estimate one of these multivariate models or hierarchical models using STAN. So we'll talk about the correlation matrix or the prior on the correlation matrix next. But are there any questions about what we've done here about repeatedly decomposing and putting more hierarchical structure on the variances, or equivalently on the standard deviations if we take the square root? So
I just missed a little bit how we came up with that the delta square of every k is how pi k.
Right. So this is just an assertion. So given gamma, I know what tau is exactly. Basically, we're just using this gamma thing to say, okay, if you multiplied all the betas by 5, then you multiply the gamma by 5, and basically your beliefs about everything have the same shape. They've just been scaled up to different units. So this gamma thing is sort of governing, the overall units. And if you scale your outcome such that a unit exponential prior is reasonable for this gamma, then that's a fine thing to do. In some cases, you might have some intuition as to what is the overall variance. In some situations, you're going to want to constrain the overall variance to be 1 or to be k or something like that, in which case you could fix gamma to 1, and this would carry over into other sorts of models. Another way of understanding this is, okay, let's say k is equal to 1, and so this is just pi is going to be equal to 1. That's the only way that you can specify one number that's between 0 and 1 and adds up to 1. So pi is now fixed to 1. You have a 1-by-1 correlation matrix, which is just, again, the number 1. So we have 1 times 1. K is 1. And so now gamma is just the standard deviation of the variability in the intercepts from one group to the next. So it's a way of doing something that works in the k=1 case and also generalizes to the k greater than 1 case, where we're specifying beliefs about a whole set of parameters that can vary from one group to the next. Roland.
How would you specify the covariance matrix if you had 10 variables rank on it? They include each rank as because I know it assumes
yeah, so you basically want to assume that these coefficients or something are also ordered or monotonic or something like that. Yeah, that would be a more complicated scenario than what we're talking about here, but you can specify priors like that, and there's an ordered data type in Stan that you can use, once we get there. But I'd say that question is still a little on the premature side. Certainly you can't do that in rstanarm. Becca?
So just like as a concrete example, we had like 2 elements, say like income and like percent not white.
Uh-huh.
If we think income is going to have much more variance than percent not white, which would make sense, that we change A.
Uh-huh.
And that's the indication that
Right.
makes it's like a larger for income.
Yeah.
And
So A for so A is inversely related. So higher values of A means lower variance. But yes, you would put a smaller value of A corresponding to the income margin and a larger value of A corresponding to the other one. But the default is just to do 1 for everything, and that tends to work well.
So how helpful, let's just say default across the board, right? And what's the point of breaking it down in all of these ways if you're just going to be like default across?
Well, the breaking it down in these ways allows us to use uniform or maximum entropy distributions for the pieces. And so that is what most people gravitate toward. But at the same time, for people who want to change this stuff, then it's relatively easy to do, and it's easier to think about like the proportion of variance, separately from the total amount of variance over all the things that you're saying varies from group to group. So it's easier for people to say, okay, like you did, the coefficient on income varies, more than the coefficient on the race thing, or maybe you said it the other way around. Either way, in relative terms, like that's an easy enough thing to think about, and at least you can get A going in the right direction. But to put it in units of absolute variance, then that's harder. And so you might want to be more vague about tau, gamma, which goes into tau and governs the overall variance thing, but more specific about the relative variances, the proportions of variances that go into pi. other questions along those lines? Okay. So that remains to specify a prior on a correlation matrix. And there is an easy, not that well known outside of the STAN community, but possibly non-informative or uniform prior on a correlation matrix that has a PDF that can be written conditional on a shape parameter eta. So this eta is not the linear predictor of a GLM, but just another scalar. Has to be non-negative, actually has to be positive parameter. In any event, this PDF is equal to some normalizing constant that depends only on eta and the size of the correlation matrix multiplied by the determinant of the correlation matrix raised to the power eta minus 1. This distribution was derived 2008, 2009, somewhere around there, by 3 authors whose names are Lewandowski, Kuro-Fishka, and Joe. But when we were trying to implement this in STAN, me and Bob could never spell Lewandowski or Kuro-Fishka. So we renamed the distribution LKJ, and so that is what is known as, even though most people who are using it in STAN don't know what LK or J stand for, much less can actually spell Lewandowski or Kuro-Fishka. So we have the LKJ distribution. It has this PDF, and eta acts much like the shape parameter of a beta distribution if you constrain the 2 shape parameters to be equal to each other. So you have a symmetric beta distribution. In any event, eta, the shape parameter, acts in much the same way, because if eta is 1, then the PDF for the correlation matrix is just going to be 1 over something that doesn't depend on the elements of the correlation matrix. So that is going to be a constant. And so we've achieved a uniform prior over the space of correlation matrices of size k that satisfy the positive definiteness restriction by construction. So that's good. If eta is greater than 1, then I is the modal correlation matrix, the correlation matrix with the most density. And it's the only correlation matrix that has any positive density as you let eta go to infinity. So by making eta be bigger and bigger, you're expressing stronger and stronger prior beliefs that this correlation matrix lambda is closer and closer to the identity matrix being the correlation matrix where everything is actually uncorrelated because the off-diagonal elements are 0. And so a lot of people are just using eta equal 1, which gives you a uniform distribution on the space of k by k correlation matrices. But insofar as you were inclined to specify a somewhat more informative prior about the correlation matrix, and often it is entirely reasonable to think that the correlations among these things are not too big, then insofar as you want to operationalize too big, you can make eta be greater than 1. You'll see people use like 4 and stuff like that. There's actually examples in the STAN manual. That seems pretty excessive to me. I will usually use, if not 1, then between 1 and 2, to give a little bit of concentration toward the identity matrix, but not a whole lot. Even if you sort of intuitively think, well, these correlations can't be all that big, you don't necessarily have a strong belief that they're extremely close to 0, or at least some of them could venture away from 0 quite a bit. If eta is less than 1, then the identity matrix is at the trough of the distribution. So it is literally the least likely correlation matrix under the prior, which is a weird thing to believe. Basically, because it's a symmetric distribution on correlation matrices, you're saying, well, I think correlations of 0 are unlikely, and correlations that are non-zero are more likely, but I'm sort of indifferent as to whether they're more likely to be positive or more likely to be negative. I just know that, in absolute value, they're close to 1. That's a pretty weird thing to think about, I think, most coefficients and stuff like that in multi-level models. So we have a good and relatively easy to use prior distribution that's built into Stan for correlation matrices. And so if we use LKJ prior on lambda, these priors on the things that go into the standard deviations, then if we do all that, we've expressed prior beliefs about sigma, but it's actually the gammas and the pi's and lambda that are primitives rather than sigma, and sigma is just an intermediate or an endogenous unknown. Questions about LKJ distribution for correlation matrices? But since lambda is a correlation matrix, it has to be positive definite, and thus it's going to have a Cholesky factorization. We can write lambda as L times L transpose. Indeed, if you declare something to be a correlation matrix in Stan, it ensures that it's positive definite by making a L and then multiplying L by its own transpose to make this positive definite matrix. And so we can write lambda equals L times L transpose, where L is a Cholesky factor. And then we can derive the PDF for L given eta just by taking the LKJ distribution and multiplying by the absolute value of the determinant of the Jacobian matrix of the transformation from lambda to L. So we're not going to go through all the derivatives on that. But this Jacobian matrix turns out to be triangular. And so its determinant is just the product of the diagonal elements, and all that is built into Stan anyway. And so it's preferable for numerical and computation, all sorts of reasons, to use L rather than lambda, but it's a relatively easy modification to come up with a distribution for a Cholesky factor of a correlation matrix under the LKJ idea. And so that's ultimately how rstanarm is working. And so we have like 4 levels of decomposition here. We're decomposing sigma into delta and lambda, decomposing the variances into tau and pi, decomposing pi into gamma squared by k, taking gamma to be primitive, taking pi to be primitive, and then decomposing lambda into L times L transpose and putting sort of the LKJ prior for Cholesky factors on L. And those defaults work pretty well, incredibly well, really, in rstanarm. Most people don't even know that they're there. But for the people who dig through the documentation and find that they're relatively easy to change a little bit in a more informative direction. And that also tends to work well. What no one does, but if they did, it wouldn't work well, I think, is to make eta values be less than 1, to make A's be less than 1, to choose like really weird values for the Shaven scale on gamma, etc. So there's certainly ridiculous values that you could choose, but there's default values that work reasonably well, and there's slight modifications of the default values in the more informative direction that also work. So questions about LKJ distribution other than how to spell the first two authors' names? So when we break things down into parts, it's easier to specify prior information in a reasonable fashion on those parts, particularly in these cases where our beliefs about the parts are basically independent of each other. If I tell you what the variances or the standard deviations or the total variance or something like that is, that doesn't really convey any information at all about the correlations. And so it's goes along with this, but when you break things down into parts, try to do so in a way where your belief about one part is not that influenced by your beliefs about the other parts, and then you can just kind of multiply everything together, and you get reasonable prior beliefs about, in this case, the variance covariance matrix sigma. All right. We briefly ran through an example on Thursday. We were running out of time, involving chimpanzees. Also, upon rereading, I realized that in chapter 12, which is what we read, is referring back to chapter 10, where this example first came up, and it might not have made a whole lot of sense or how it applied to social science. Anyway, this was a study. I don't think it was done by McElrath himself, but someone who studies chimpanzees and whether they were pro-social or anti-social. It involves having like a chimpanzee around here, and there's two levers, one on the left, the other on the right. In this way here, the one on right has 2 boxes of food, and the one on the left has 1 box of food. And so the chimpanzee chooses to pull on either the left or the right, and that opens up the boxes, and there's a spring here. It sends 1 box of food to the chimpanzee at the other side of the table, and then 1 box of food this way. We can choose the one on the left, in which case it sends the box of food towards the chimpanzee down here, but there's nothing in the box of food that goes to the other chimpanzee. And so you can vary whether the 2 boxes of food are on the left or on the right. You can vary whether there's another chimpanzee to begin with, or whether it's like a friendly chimpanzee or an enemy chimpanzee on the other side of the table. All sorts of things that you can vary in the context of this experiment. And researchers in this have found that when chimpanzees do this experiment, they behave a lot of the same ways that sophomores do when you do this experiment on them. So it actually does have some applicability to experiments in economics and in sociology. So all that said, you can download the data from his GitHub repository, and in rstanarm you can call the stand glimmer function to estimate a multivariate model. Pull the left one is a binary variable indicating whether the chimpanzee pulled the lever on the left. That depends on various experimental conditions that were manipulated by the researcher, or exclusive, but there's another variable that says, are the 2 boxes of food on the left or on the right? So they didn't want to systematically do that. So that was randomized as well. So basically all the experimental conditions interacted together, and we want to allow the intercept for the log odds as well as all the coefficients on all the main effects and the interactions to vary according to the chimpanzee who sits here. So they did this on a number of chimpanzees. And so we want to allow chimpanzee to chimpanzee variation and how to do this. And, you know, the chimpanzees got several different tries with several different experimental conditions. So we observe the same chimpanzee a number of times. So in this particular case, it might be somewhat reasonable to think of this multi-level model from a frequentist perspective, because we could have taken another chimpanzee from the population of chimpanzees. So this experiment didn't exhaust, you know, the entire population of chimps. But we can, you know, just as well think of it from a Bayesian perspective, prior beliefs about how much the intercept and the coefficients vary from one chimp to the next. And this, you know, certainly generalizes to other situations in which it doesn't make sense to think about like the levels of this factor as being random draws from some population of chimps or schools or whatever it may be. Binomial, because the outcome is Bernoulli. QR equal true, because we're, you know, going to stick with the default prior on all this interaction stuff. There's another argument, prior underscore covariance or something like that, in which you can specify the elements of the prior that go into, you know, all this stuff, but we're going to leave that at its default values. Go ahead, run the thing. We get 4,000 draws on 42 margins of this posterior distribution. Robert.
What's going on with the Lewis syntax here?
Okay, so this is saying there's an interaction between all the other conditions of the experiment and whether the two plates of food were on the left or on the right. So all that got randomized. Yeah. So like, do you know this chimpanzee? Is it a stranger chimpanzee? Like all stuff that you could imagine being randomized or blocked on in a experiment.
What about the second one?
Then this line here says basically let all the parameters also vary by actor. And so this, all this stuff, the way we had it represented last week is going to go into X. So there's sort of overall chimpanzee behavior. And then from one chimpanzee to the next who's sitting at the near end of the table, there's variability. And the variance covariance matrix is calculating the, or capturing the variability in all these coefficients across one chimpanzee to the next. Okay, this is just, actually the one is included by default. I was just being explicit here. This is saying allow the intercept and all these coefficients to vary by actor, as opposed to what we started with, you know, just allow the intercept to vary. If you did -1 here, it would say keep the intercept the same from all chimps to the next, but allow the coefficients to vary from one to the next, which is probably a little bit of a odd thing to believe. So certainly you see a lot of frequentist models where they're only allowing the intercept to vary. And that's not because that, you know, makes a whole lot of sense scientifically. You think, well, okay, if the intercepts can vary, why can't the coefficients? But doing a model with frequentist optimization, it's much harder when you allow the coefficients to vary group by group than just the intercepts. So they'll just, you know, make the assumption, well, there's no variation in the coefficients from one chimpanzee to the next according to this. You might go a step farther and say, well, maybe the standard deviation of, you know, the errors, if this was a Gaussian model, maybe that varies from one chimp to the next and have some sort of a specification for the error standard deviation. You can do that in Stan. You can't really do that in rstanarm. But all these things that are sort of hard to let vary if you take the frequentist perspective and just do optimization to find the mode of the likelihood are pretty easy to do if you just step away from using optimization and use MCMC in order to get draws from the entire posterior distribution, which in this case has 42 dimensions. So, Jonathan.
I'm wondering a little bit what you mean about it's difficult to do this perspective. Because, for example, you can like use the same code basically with a frequency.
Oh yeah. So if you took off the stand and
Right.
and did this in LM4, yes.
So
It's easy to specify the syntax.
Yeah.
It's hard to find the maximum. Much harder to find the maximum. You could get stuck at a local maximum, saddle point, or the most common affliction that you see when trying to do this by optimization is that you get an estimate where one or more of these variances are 0, or the correlation matrix or covariance matrix is singular, which is to say it doesn't have an intercept, which is right on the border between positive definite and indefinite. And so you get these optimums that are on the edge of the parameter space, which one, doesn't make a whole lot of sense usually, and two, invalidates like all the frequentist inference you can do after this. One of the assumptions that justifies such inferences is that the parameters have to be on the interior of the parameter space, and so you can get a multivariate normal sampling distribution around them. If one of the parameters is 0, you can't be multivariate normal around 0 if you're a variance. You can only be on the positive side of 0. And so the whole idea of a multivariate normal sampling distribution from one study to the next does not hold in that case. And so you get warning messages, you get corner solutions. It's usually pretty bleak, unless you're just allowing the intercepts to vary, and then, you know, things go reasonably well, but you don't have a particularly persuasive model. So we get the output. You can see here that individually, so on each margin, we have a considerable amount of uncertainty about all of those, and that's just the way it is. There were 504 observations, so that may seem a little bit surprising, but is, you know, maybe more surprising or less surprising when we consider the error terms, which are really only error terms from a frequentist perspective. But we have, you know, posterior medians of the estimates of these things. So the intercept from one chimpanzee to the next was estimated to have a standard deviation of 1.63, or at least that's the posterior median. Whether the thing was on the left or the right, that has a standard deviation of 0.76 on that parameter. The experimental condition pertaining to the identity of the other chimpanzee, you know, all of these have relatively large standard deviations from one chimpanzee to the next. We also have estimates of the posterior medians, I think, of the correlations in all these parameters from one to the next. It's just showing the lower triangle of this correlation matrix here. And we can see that these posterior medians of the correlations are certainly not that large, but they are certainly, well, maybe this one, but some of them certainly are well away from 0. And so it wouldn't make sense to have, you know, independent beliefs about, let's say, you know, the condition and whether the thing is on the left when those things are correlated in the posterior distribution, -0.23. So for better or for worse, that is how we would estimate, you know, one of those models. So I wanted to show you how you would take the example from the reading and do it in rstanarm. Rashika.
The last line in the after 7, does it mean that there was 7?
There were 7 chimps who sat at the bottom of the table.
So based on that, I'm trying to estimate the number of variables. So it's 7 times 3, right? Like 1 into 7. 7 times
Let's see. So there's 4 choose 2. So 1, 2, 3, 4, 5, 6. Then there's 4 more here. That's 10. And then there's 1, 2, 3, 4 of these times 7 chimps. So 28 plus 4 is 32 plus all those comes out to 42-ish. I mean, it comes out to 42, but there may be some other things that are being estimated that are not shown here. But most of them come from 1, 2, 3, 4. And then there's 1 per chimp times 7. So that gets you to 28. And then there's another 14 somewhere. Jonathan.
So you're saying that because the prosocial condition or the prosocial parameter and condition are negatively correlated in the posterior, that it would make sense to apply effect?
No, that's fine. Like, even if we were doing this frequentist, it's fine to say, okay, my estimate of those things is negative 0.23. But in light of that, it does not make sense to proceed as if negative 0.23 is 0, and you have, independent beliefs as to how these things vary from one chimp to the next. And so if I told you, okay, the 2 plates of food are on the left, that should influence your beliefs as to how, the coefficient on condition, varies from one chimp to the next.
So are you supposed to go back and update your house based on results?
No, this is just the posterior distribution. This is what you believe now. If you were to do the experiment again, or you were to bring in more chimpanzees or whatever, this could be, the basis of your prior extending that forward. You can do posterior prediction. Here we're just doing it for the first chimp. We can specify the exhaustive ways of which condition can either be yes or no, and the thing can either be on the left or on the right. We can get probabilities, posterior probabilities, as to whether that chimpanzee will pull the one on the left, and we can see how this varies depending on what the condition is. And so even though marginally we had large standard deviations here, when they come out and go through the whole nonlinear transformation into probabilities, yeah, we can say that there's a pretty clear difference between scenario 3 and scenario 4. So in both scenario 3 and 4, condition is 1, whatever that means. I think it means the other chimpanzee at the other side of the table. And then is the 2 plates of food on the left or on the right? Left if it's 1, 0 if it's right. And so the probability that the chimp in that situation pulls the lever on the left, the median and the mean are up above 0.5. Whereas, if one of those things is varied, then you can get different sets of probabilities here. And you can subtract, one column of probabilities to the other to see the difference in probabilities depending on what scenario you're talking about, and you can get a posterior distribution on that difference. So we can do all that. We can get the ELPD. But remember, the ELPD is the estimate of what would happen if you were to drop the ith observation and evaluate the likelihood, or do the whole thing with the remaining observations and then predict the left out observation. And all that involves the likelihood evaluated over the posterior distribution. But in multi-level models, there's a question of which likelihood do you want to use. Is it the likelihood function of beta, b, and everything else together, which would be the product of n univariate normals? or is the likelihood just, you know, beta, sigma, L, etc., with the B's integrated out, which is the likelihood that frequentists use when they're doing maximum likelihood estimation. Either of those is legitimately a likelihood function, so you have to choose which one you want to do in order to calculate the ELPD. And this choice depends on whether you imagine, am I leaving out one observation or am I leaving out one chimp? Do I want to make predictions for what the existing chimp would do if we, you know, extended the experiment with that chimp another observation, or if we left the whole chimp out and then predicted what would happen in the experiment for the left out chimp? So are you leaving out observations with the same groups, or are you leaving out a whole group? That governs which likelihood function you want to do. Now, what Lou currently implements is the thought experiment where you're leaving out one of the 504 observations, but keeping it, the predictions confined to these 7 chimps. But the other way, integrating out the group variables, is arguably better if the criterion that you have utility on is, can I predict a future chimp better for the whole raft of things? And there's a video from Stan Kahn going into these differences. In any event, here we're talking about leaving out one of the 504 observations. We can see, you know, here all our Pareto K estimates are, you know, less than 0.5, so things are looking good. If we had another model to compare it to, we could use the ELPD to do that. So, you know, that all carries over, but you got to think, am I leaving out a group or an observation within a group? Okay. So remaining time today, we want to talk a bit about VRMs, and to just sort of set this up, the thing about the workflow for how you use Stan via R. So someone writes, or something writes a program in a text file that ends with a .stan extension. And this has this sort of Stan, which is vaguely R-like syntax that defines a posterior kernel in log units, and then this gets translated to C++, compiled into an executable, and it does no U-turn sampling and stuff like that. We're still not going to get into this idea of writing Stan programs ourselves until next week. What rstanarm does is it comes with Stan programs that are written by hand, and they're compiled into executables on CRAN, and at least if you have Mac or Windows, then you can just download those precompiled models from the rstanarm package, and they're ready to run. So what VRMs does, which is another R package, it generates Stan files in the temporary directory from the R syntax that you give it, compiles them, and then, you know, draws from their posterior distribution. And so the difference between these two, like rstanarm is a lot like going to Best Buy and, you know, buying a laptop from there. You just sort of walk to the aisle where there are laptops, and you pick one off the shelf, and as a consequence, the models that are the laptops that are on the shelves are, you know, sort of general purpose, you know, useful things that the sort of people who wander into Best Buy to buy a laptop would be interested in buying. But they don't have really that much customization to them, you know, other than, you know, you can change the priors around a little bit, but the priors that are offered are certainly, you know, you only have a few choices there. Whereas VRMs is more like ordering a laptop online. And, you know, if you buy a laptop from a reasonable online place, you have all sorts of options to customize the size of the hard disk and the RAM and basically everything else. And then when you enter in your credit card, some robot assembles your laptop with the parts that you wanted to pay for into the laptop, throws it in a box, and then sends it to you by FedEx. And so VRMs is really putting together a Stan program from pieces that are implied by the implied by the R syntax that you specify. And then the binary gets executed. This is done by the VRM function in the VRMs package. And then you can diagnose, analyze the resulting samples from the posterior distribution that are provided by Stan in much the same way, whether you're using VRMs or you're using rstanarm. So that's a little bit of an overview. Another way is to look at this figure from the reading. So the user passes all formula data, stuff about the priors to the function VRM. VRM internally calls a function. These are actually exposed. Make Stan code, make Stan data. Then the code, the data, etc. These are passed to the rstan package. The rstan package will translate it into C++, compile it, and then fit the model using Stan. There's a little bit of convenience stuff that is done after the fact in order to make associate names and stuff, which is with each of the parameters, and then the results are investigated by a human using the R methods that are defined for an object that is produced by the BRM function. Whereas, rstanarm, there's sort of, human does all this stuff relating to Stan, and the user basically just passes the formula and the data to these R wrappers around precompiled Stan functions, and then the last couple steps are basically the same. So what is this VRM function? Unlike rstanarm, where we have like Stan underscore LM, Stan underscore GLM, Stan underscore GLMER, a whole bunch of different functions that are designed to look like, at least the essential parts, other functions that are popular and being used for frequentist estimation. The VRMs package basically only has one model fitting function, and that is called VRM, and consequently it has a lot more arguments because you're specifying a great variety of models through this one function. I haven't counted exactly, and probably depends on how you count, but it wouldn't surprise me if you could estimate what frequentists would consider more than like 1,000 different models just using VRM and Stan ultimately. It's certainly in the hundreds, but 1,000 wouldn't really surprise me. So there's a formula, there's a data frame that contains the variables in the formula, there's a family which basically specifies the likelihood. There's this prior thing, which we'll talk about in a second, where you specify the priors on all the parameters in the model using Stan syntax, and there's a whole bunch of other arguments that pertain to particular characteristics of particular models that can be estimated via the VRM function and using Stan as a backend. So it would not surprise me if almost all the models that you are interested in estimating could be estimated using just the VRM interface to Stan. Most but not all could probably be estimated by rstanarm, but almost all regression sorts of models can be estimated by VRM. And so this was basically the dissertation of this guy, Paul Christian Berkner, who put all this together, and even after he defended, has kept adding more and more things to BRM so that you can basically be estimating pretty much any regression model. So the formula argument, everything to the right of the tilde is basically the same as Stan underscore glimmer, which is basically the same as the LME4 package. However, In the case of BRM, you can have more stuff to the left of the tilde than simply the outcome variable. Oftentimes, you just have the outcome variable. But with BRM, you can actually estimate models that have multiple outcome variables. And there's some additional syntax for estimating even models that only have one outcome variable using another vertical bar thing. So to the right of the first vertical bar and to the left of the tilde, you can have sense and trunk to indicate whether the outcome is truncated. If you're doing meta-analysis, you can specify the standard errors of the underlying studies that you're meta-analyzing. If you're doing binomial model, you can specify the number of trials. If you're doing an ordinal model, you can specify the number of categories, all things that have these special functions associated with them. And if you want to use any of these, then if y is your outcome variable, you just do y bar, cat, whatever, tilde, the variables that go into your ordinal model. You can do this stuff with another LME4 thing, allowing some of the parameters to vary group by group, specify your data, and then family is one of the things that implies a likelihood for an ordinal model. And so the reason why you can estimate hundreds, if not maybe 1,000, somewhat different models using VRM is because it has a lot of families and link functions that can be used for a model like that. And you can do these sorts of things if you're piecing together different parts of a model on the fly, whereas it's a lot of work to write out a stand model, to put into rstanarm for each one of these things if you have to write out the thing by hand and check it. What BRM is really doing is it's generating design matrices and it's applying transformations, and it's got a whole bunch of likelihoods and stuff here, and it's just it has little snippets of code where it can like a robot assembling a laptop, assemble it into a stand program that you don't even see in ordinary usage, and then translate it to C++, compile it, etc. There's also BRMS family, where you can just put a name of one of those things, and it does the same way. And so this covers basically all the same things that you can do with like stand glimmer, plus a whole lot more families, likelihood, link functions that we have not implemented yet in rstanarm, and certainly we're not going to implement every single one of these. Okay, so bigger. There we go. So the prior argument, unlike rstanarm, where we have like prior intercept, prior and on the coefficients, prior on the covariance matrix, prior on the auxiliary variable, etc. There's only one prior argument in BRM, and it sort of takes a list which specifies the prior distributions you want for all the parameters in the model. And he has this set prior function which facilitates specifying such a list. So when you call set prior, the first argument prior is a character string specifying the name of the distribution and the parameters that you want to use using the stand language. And so normal 0.5 indicates a normal prior with an expectation of 0, a standard deviation of 5 on whatever you're talking about. The next argument, if you specify it, indicates the class of parameters that the prior character string applies to. So if you do B, that means this pertains to all the regression coefficients. But you can modify that more by specifying some of the other parameters. And so you could say, okay, this only applies to this, the deviations on this grouping variable. If you have a model with multiple outcome variables, you can say, okay, this applies to the coefficients in the first outcome variable rather than the second outcome variable. You can have lower bounds and upper bounds on the parameters, but those default to infinity. So all sorts of things that you can do like that to specify what your prior is. There are default priors for a lot of things. When VRMs first came out, there's a lot of default improper priors, but that has changed for the better, and that by now most of the things have a proper default prior. And you can see what those are by calling the get underscore prior function and specifying what your model is, inclusive of the data and the family. So here we have log normal likelihood, some sort of a duration model. We have a binary variable indicating whether the events are censored. And then we have all sorts of characteristics about the patient, including allowing the intercept and the coefficient on age to vary from one patient to the next. But if we call the get prior function, it spits out a printout of what priors would be used by default. You can save that, modify it, customize it however you want. So we have priors on the coefficient on age, the interaction between age and female, the disease is a categorical variable, etc. Main effects for gender. Those are all going to be by default improper, so there's nothing there. There's a 2x2 correlation matrix on how these vary from one patient to the next. That's LKJ with the shape of 1, so that is going to be uniform. Then the standard deviations on these sorts of things. They have priors, which are student T with a small degree of freedom, 3, and also the intercept in this model is going to have a student T prior as well. There's no bounds, and then the overall standard deviation of the log normal has a sigma parameter that is also going to be student T. So a lot of the default priors on standard deviations and stuff like that, they tend to be half T distributions with a small degree of freedom so that their tails are pretty heavy. Anyway, you can read about all what the default priors are and change them using, get prior and set prior. So we'll come back to the hypothesis thing. But anyway, you compile, you run, eventually you get back posterior draws. And then many of the things that you can do with the objects produced by the VRM function are analogous to the things that you can do if they were produced by rstanarm. So you can call launch shiny stand, you can use base plot, you can use Loo, you can use bridge sampler, you can use post-prob or whatever to get posterior probabilities on models. All these sorts of things that you could do with rstanarm output, you can basically do with output from VRM, and maybe a few additional things, but we'll have to talk about those on Thursday when we actually do an example using from start to beginning the stuff in the VRMs package. Okay, so that is it for today.